Let's take a moment and apply the limit definition of a derivative to a radical function. In this case, f of x is equal to the square root of x. So once again, we will work on our substitutions. So we're going to have limit as delta x approaches 0 of the square root of x plus delta x minus the square root of x, all divided by delta x. That gives us f of x plus delta x minus f of x, and again we divide all of that by delta x. So what we have here is something where if we try to plug in 0 for delta x, we get the square root of x minus the square root of x, which is 0, over delta x, which is 0. We get one of those 0 over 0 indeterminate forms, and that happens pretty much every time you try to use the limit definition. So we have to do some algebra to try to figure out what we're going to do here. And since we're dealing with radicals, a good choice is often to use a conjugate and see if we can rationalize something. So let's multiply top and bottom of this expression by the square root of x plus delta x plus the square root of x. And we'll do the same thing in the bottom, square root of x plus delta x plus the square root of x. And let's see if that helps us at all. So we're going to have the limit as delta x approaches 0. We're going to end up with x plus delta x minus x when we do that. Remember, essentially what we're going to do here is a double distribution, or if you're used to the idea of FOIL, you can think of it that way. We're going to multiply the two square root of x plus delta x's together. That gives us just an x plus delta x. We're going to multiply square root of x plus delta x, in the first expression by the square root of x in the second expression. That gives us a plus square root of x times square root of x plus delta x. But then we're also going to pick up a negative one when we take the negative square root of x in the first expression multiplied square root of x plus delta x in the second expression. Those things will add to 0. They disappear. This is the point of using a conjugate, and this is the nice result that we get every time. Finally, we multiply a negative square root of x by a positive square root of x, and we just get a negative x. This is all going to be divided now by delta x times the square root of x plus delta x plus the square root of x. Now you may have already started to notice that in the numerator we're going to have a positive x and a negative x. They're going to disappear. So we're going to have the limit as delta x approaches 0 of just delta x divided by delta x times, once again, the square root of x plus delta x plus the square root of x. Those delta x's, top and bottom, common factor. We can cancel them. That will leave us with the limit as delta x approaches 0 of 1 over the square root of x plus delta x plus the square root of x. So as delta x goes to 0, we're going to get a square root of x in the first term in the denominator. We already have a square root of x for the second term in the denominator, so we're going to end up with 2 square roots of x. So we will have the limit as delta x approaches 0 of 1 over 2 times the square root of x. Actually, I can remove the limit at this point. We didn't need the limit, we were taking the limit. So my apologies for that extra little bit of notation there. The derivative is equal to this expression. So for any point on the curve, any x value in the domain of f, plug it into this derivative function, 1 divided by 2 times the square root of x, and you will get the slope of the tangent line at that point.